Hello students, welcome to the 46th class in linear algebra. In this video lecture, I will discuss a very important theorem which states that let T be a linear transformation which is defined from a vector space V to W, right? And then I have to prove that the following statements are equivalent to each other. So the first statement is if T is non-singular, this implies T is 1, 1. And then if T is 1, 1, it implies if B is a linearly independent subset of a V, which implies that T of B is a linearly independent subset of W. And similarly 3 will imply 1. So if I consider the third statement, it will imply that T is a non-singular. So let us prove this theorem step by step. So first I consider 1 implies the 2. So what was 1? 1 is that T is non-singular, right? And what I have to prove? I have to prove, so to prove that T is 1, 1. So in order to prove that T is 1, 1, so I will use the fact if two images are equal, it means the elements have to be equal. So let T of V1 equals to T of V2, right? So that is for V1, V2 coming from V. Now if two images are equal, so because T is a linear transformation, can I say that is T of V1 minus T of V2 equals to 0? And now because T is a linear transformation, can I say from here that is a T of V1 minus V2 equals to 0? Now I have to use the fact that T is a non-singular. So if T is a non-singular, it means V1 minus V2 equals to 0. So that is the by the definition of non-singular. So which implies that V1 is equals to V2. So you considered T of V1 equals to T of V2 and finally you proved that V1 equals to V2. So which implies that T is 1, 1. So this implies that 1 implies 2. That is if T is non-singular, so you prove that T is 1, 1. Now similarly you have to prove that 2 implies the 3. So what is 2? 2 says that T is 1, 1. And what is the 3? 3 says that if B is a linearly independent subset of V, which implies that T of B is a linearly independent subset of W. So that is what you have to prove. So in order to prove that is a 2 implies third, I will consider V equals to V1, V2 up till so on to Vn be a linearly independent subset of V. Yes. Now what you have to show? You have to prove that is the collection of the images, that is a set of images, that is T of V1 comma T of V2 and so on to T of Vn. So you have to prove that this is a linearly independent subset of W. Fine with this? Now again, use a similar approach. Whenever you have to prove something to be linearly independent, what do? I'll consider the linear combination. So consider that is alpha 1 T of V1 plus alpha 2 T of V2 up till so on to alpha n T of Vn is equals to 0, right, where alpha are the scalars, right. Now since T is a linear transformation, so can I say this is alpha 1 V1 plus alpha 2 V2 up till so on to alpha n Vn, and 0 can be written as T of 0 because T is a linear transformation. Now what you have to do, you have to use the fact that T is 1, 1. So if two images are equal, it means the elements have to be equal. So you have to use this fact. That is because T is 1, 1. So that fact you have used up here. Now, since this set B, what is the set B? Which is containing V1, V2 up till so on to Vn. And this is a set which is a linearly independent. So by the definition of linearly independent, so if the linear combination is 0, so this implies all the scalars have to be 0. Why? Because the set capital B is a linearly independent set, right? And hence what I have proved that T of B is a linearly independent subset of W. That is, we considered T to be 1, 1 and then I proved the third part. Now I will prove 3 implies 1. So I will consider that this statement holds and I have to prove that T is a non-singular. So for this you can watch my previous video, right? Link added in the description. In that I have proved this theorem in the converse section, right? So you can watch that section and hence this theorem will be proved. So I hope this video lecture is clear to you now. In case if you have any difficulty, you can mention it out in the comment section. For more such videos, do subscribe to my YouTube channel and do not forget to press the bell icon. Thank you so much, students. Thank you.